All right, good morning. Thanks. My name is Brett Newman. I'm part of the consulting services group at NCAR, and I'm going to be talking about profilers, and in particular, I'm going to be talking about NSight systems. So the first thing I'll present is a scenario that you've probably been in before where you have a code base that you need to get up to speed up quickly here, and maybe you need to make performance, maybe you need to performance changes, maybe you need to port the code to the GPU. Maybe you just need to make some decisions in a timely fashion. So if you're in this situation, a profiler is usually a good place to start. And the profiler is going to give you information about the flow of the structure of the code, but it's not going to give you any sort of idea in like decision making of the code and what changes you should make to improve the performance. So it's important to note that it's just going to provide information to you to lead to more efficient use of those resources for your code. It's also important to note that these profilers usually end up adding a significant overhead to your application, so be mindful of that before you launch that on some 200 node job. So how do we get there? First step, obviously, you're going to profile your code. What you need to do that is to set up a baseline, and the baseline is important for our performance metrics here. We need to use a baseline as a way to compare the changes that we're making are actually beneficial. So performance is relative, and we need to make sure that that baseline is a realistic run of your application. So you need real data, and you're going to need a reasonable runtime. So once you get that baseline set up, you're going to look to make potential performance gains using those tools. You're going to try and use your experience, and then also dealing with the constraints of your system. So some of the constraints that you'll deal with are going to be clusters. You'll be operating different clusters you're running the code on, maybe hardware architecture, so CPU, GPU architectures, maybe even distributed network types, memory limitations. You have to deal with flow control. So are you dealing with a lot of simple instructions that are better on the GPU, or branching instructions that are better to be run on the CPU? You have to deal with programming language differences, and probably most important is going to be development time. The tools, like I said, they can give you insight, and in particular, sections of code that are using up significant runtime. So a lot of times there's a function you'll notice right away that's taking up the most runtime, but it's not always the highest potential to optimize that function. So just keep that in mind as you're looking at your profile reports. So there are a couple data collection methods that we'll be going over in our example. And the first is sampling, which is just collecting the state of the application at regular intervals, or the sampling frequency, and understanding how much time is being spent in a function. There's concurrency collection methods, which that's identifying shared resource bottlenecks, communication overhead, and thread or kernel inefficiencies via call stack traces. And then memory methods, which gather information about data movement, allocation, and resource availability. So the example that I'll be going through here is going to focus on profiling code on NVIDIA GPUs on clusters in the role of a researcher. So our interest is going to be primarily in performant threads, kernels, GPU utilization, and memory efficiency. So we're going to talk about NSight systems, which is the maybe higher level GPU profiling tool that NVIDIA offers. And we've seen this chart before, but this is going to give you an idea for the process flow. So NSight systems, you're going to give you visual algorithms, ideas on how to optimize the synchronization, how to deal with data movement and improve that, and how to improve parallelization. So there is a recommended profiling model from NVIDIA, and it's based on the client server model. And we'll follow the flow chart here, where the server is likely going to be the node where you're running the code on, so on a cluster somewhere most likely. And in this spot, you're going to identify the code to be profiled. You're going to actually launch the profiler. So we're going to record the application on the server. From there, once you have the report generated, it's easiest to transfer that to the client, which is likely your local machine. You're going to analyze the generated report there. From there, you can make decisions on NSight systems and NSight compute on what sort of performance changes you want to make. After that, you go back onto the server or the node, and you're going to implement those changes and repeat that cycle until you're happy with the performance or optimizations that you've made. So before we start into the actual example, I want to clarify quickly that a GPU kernel is actually generated when previously we had ran ACC directives on the mini-weather app. And so when you set a flag for the ACC parallel loop, what's actually going on behind the scenes is the compiler is going to generate an NVIDIA CUDA kernel. And so when we see that in the profiler views later, that's what's actually happening is these OpenACC are getting converted to GPU kernels, and we're analyzing those. So the mini-weather app OpenACC profiler, we're going to start out here first with the baseline. So the idea here is we have the mini-weather app, and we are going to try and port this to the GPU for the very first time. And I'm going to approach this in a very naive way. And I'm going to go and look through the code and identify some loops within subroutines. And I'm just going to try and use ACC directives to turn those into CUDA kernels. So I don't really know any better, so I'm going to just set up ACC loop parallel with no additional help or hints to the compiler on how to deal with those loops. So this is our baseline. This is just going to be a realistic run that we're trying to set up that we can compare our optimizations to later. So you can see here, I've highlighted in the image, this is the subroutine semi-discrete step, and there is a nested loop that I've highlighted down below, and I've just set the flag for ACC parallel loop. So from here, we're going to compile the code. We're going to get it ready to be profiled. And to actually set up the profiler, we're going to use the nsys command and the subcommand and profile. So you can see the command line launch to actually profile the application here. In nsys profile, we're going to profile the app. The -O, we're actually setting up the name of the report. So in this case, we have the mini-weather baseline, and it's important to do that because we're going to be looking at quite a few reports and comparing them back and forth. After that, we've got the actual application we're going to run, and then the -T is the trace. So what we actually want to trace in the application to try and seek optimizations on. So going through the notable flags quickly here, trace I just talked about, but there's some additional options that are of interest, the cuBLAS, cuDNN, NVTX, which I'll cover a little bit more later, OpenACC, which we're particularly interested in, and then MPI is another one that you might want to add. So there's also backtrace, which is enabled by default. That'll allow you to do some sort of call stack analysis, which we'll look into a little bit more later. There's a memory usage parameter where you can get the GPU memory usage information. There's MPI if you're going to start looking at multi-node GPU sort of optimizations. And then stats, which if you're just going to look at things in the command line interface, that might be the way to go. I encourage you to look. There's some commands here if you're following along. The nsys-h, that'll be the help file that gives you a lot of information on the other flags that you can use within NSys. And then the subcommands, NSys profile, you can also get information about those subcommands. So here we would launch the profiler on Casper. After that's completed, you'll see the qd-rep file that is the actual report. So that is the profiler running and generating this file, which is the report that we're going to look at. And if you just wanted to get some quick information and stay within the server, you can do the NSys stats on the report itself. So here, if we run this, it's just going to give you a really quick overview of the CUDA API call section here. Below that, you have the CUDA kernel section. And just to note that that'll actually give you the total runtime of that kernel within the application run. Below that, you're going to actually have the memory movement, so the memcopy operations in these next two sections. And then below that, you have the OS calls as well. So if you've seen NV-prof before, then this looks very familiar. You can do a lot just within the command line interface just to get an idea of what functions are taking up a lot of time in the code. But from here, we're going to move on to the timeline analysis via NSight systems. And the first step here is going to be to actually transfer the report to your local machine. You can actually launch an X or VNC session on Casper. I just have found that to be a little bit slower than running these on the local machine. There's a lot of zoom in and out, and the lag can be a little bothersome. So Here we've generated the mini weather baseline.qd rep file. You can just go ahead and download that. That's in the reports folder from the Jupyter Hub browser on the left if you'd like to follow along. So if you launch the NSight Systems GUI, you'll be prompted by this window, and we'll go on and take a look at the projects section, which this will be an important area on the left pane that I've highlighted. This project is going to keep track of all of the profile reports that you've run. So if you wanted to do a different set of optimization attempts, you'd create a new project, and then you'd have a new set of these reports that you could go through quickly and keep things organized. From here, just to get familiar with the navigation of NSight Systems, you have on the top the open reports. This you can quickly switch between the baseline or some optimization that you made and do the analysis visually here. On the x-axis at the top is the application runtime. That's the wall time, which will be a useful metric. On the left middle, you have the collapse or expand for our detailed views. So we'll be looking at the kernels in more detail later. And then the timeline control, you're going to be using a lot, which the zoom in and out, you can either do command plus or minus or command mouse wheel up or down to quickly zoom in and out. You can also look at the event descriptions here. You've got a couple things that you want to keep track of, which is the CPU utilization, the runtime traces that we've set in the profiling, and you can see that there's OpenACC here, which we set when we ran that profiling command. And then there's the GPU kernels, which we'll be looking at more. So real quick, this is the report that we just generated for the baseline, and this is the completely zoomed out version of it. So you can see our runtime is 330 seconds. So that's a good runtime. But before we do any additional sort of analysis and try to optimize the code, I want to talk about a few things here. So we'll take a look at this image and we'll talk about patterns, gaps, wall time, and kernels. And patterns in the code are going to be a helpful landmark as you're trying to optimize things or make changes if you don't know where to start. And I've set brackets up in a pattern that I've seen in the code. So you can kind of see this set of 3 pattern that's going on over and over again. And I've taken note of how long that pattern takes to complete. So this, if you look, takes about 20 milliseconds to complete. And we're going to use that to see if we gain any performance on these particular patterns that we're seeing as we make changes. You can actually see on the left of the pattern, there is a section here that is considered a gap, and that's when the GPU is idle. And generally speaking, that's a bad thing when you're trying to get GPU performance gains. So keep that in mind. We'll look at that a little bit later in ways that you can try and reduce the gaps in there. And then, like I mentioned earlier, wall time is also a useful metric. That top x-axis view is going to be something that we'll use as well. So the kernels you can see here, I've expanded out the kernels section, and these are actually the kernels that get generated, and you have specific kernel calls, each one of these blocks you can see. Another thing I like to do if I don't know where to start in terms of optimizations is look at this stats view, which is below the timeline view. A little drop-down menu will give you some idea just what instructions are occurring, how long we're spending in those instructions. And I've highlighted this particular instruction because it seems to be taking up quite a bit of time in the application. So this is the CUDA stream synchronize instruction that's being called, and it's spending about 311 seconds. So that might be an indicator on our plan to optimize on the next step. So as we can see, if we look, we've actually checked out the CUDA summary section of the stats system view, and that's combining the CUDA API calls and the kernels as well, and some of the memory operations. So we're still looking at about 50% of the runtime to spend in this CUDA stream synchronize. So to me, that means that we're actually waiting to synchronize outside of streams. So we're not taking advantage of pipelining within the GPU. So we're going to make changes to that ACC loop parallel section, and we're going to add an asynchronous clause in there. So we're going to go back into the code. We're going to go through these loops. We're going to modify those loops. We're going to add the asynchronous clause to it. We're going to recompile, and then we're going to profile the application again. So profile command is very similar. NSys profiler. We're going to change the name of the report so we can ID it, mini weather async, and we're going to launch that again. So once we have that report, we can convert that or transfer that back to our local machine. We'll take a look at that QDREP file again. And we'll notice right away, if we look at the stats system view here, the total time for those synchronized events didn't really change much. So we didn't get much of a performance benefit, but we did notice that the CUDA stream synchronized changed the CUDA context synchronized. So to me, that indicates that we're actually achieving some sort of pipelining here, that the actual memory operations and the instructions are running within the same stream. And if we wanted to confirm that, we can go in and look at the timeline. And you can see on the left, I have the mini-weather baseline report, and on the right, I have the mini-weather async report. So you can see stream 14 here on the baseline is actually going to be separate memory operations from the stream that the kernels are launching on. Whereas you look at the async operation, you can confirm that the memory operations are occurring in stream 14, which is the same stream. So that's a good sign. We actually can confirm our async changes. But to note, we're still spending a lot of time in that context synchronize. So what's the next step here? If we're spending a lot of time waiting for synchronization, is the OpenACC best practices would be to try to parallelize our loops. And so why don't we try and do that and use the collapsed loops clause to try and go through our loops again, modify the code. We have a nested loop of the depth 3, so we're going to use collapse 3. We're going to collapse that loop. We're going to go ahead and compile the code again and profile it again and see what ends up happening. So same thing, NSys profile. We'll change the name again, clarify that it's the collapse version, same traces. And we'll go in and we'll take a look at the report on our local machine again here. So this is the async collapse report. And right away, if we look at the image, we can see wall time has changed significantly. So previously, our wall time was around 330 seconds. So we've gone down to 41 seconds. And that's a pretty decent performance gain here. So we can also inspect the stats view. We can identify that we're spending a lot less time in this CUDA stream context synchronize. So one thing to note here is that on the previous report, that async report, we were able to actually look at a specific instruction. And so in the CUDA API instruction, if you hover over this instruction, you'll get this little identifier that gives you, this is a CUDA driver API call, and it'll give you the time it took to complete that instruction. So this is about 15 milliseconds. And if you do the same thing and we look at the collapsed loops version, you can go ahead and see that that's down to about 1 millisecond. So that's another way to just visually see that you're getting some sort of performance gain. Another thing to note is that we're actually getting some additional kernels being launched in between synchronization. So to me, this means that yes, that we're achieving much better parallelization of these kernels. So if you hover over, you can see these events, these kernel launcher events are being launched in between the synchronized events. So that's a kind of the process you would go through to make changes, to recompile, and then look at those reports and compare them against the baseline and see if you can get some sort of optimization out of it. So another thing I had mentioned before is this idea of a gap, and there are significant gaps. If you look at the timeline, you can see these gaps where the GPU kernels are idle. And you can actually go and hover over some of these events that are happening right as the GPU idles. And in this instance, I'm looking at an IO operation. This is open, the OS. And you can, I know this is probably pretty small to look at, but you can see if you follow this call stack that this is getting called by the mini-weather output subroutine. So this is an IO operation, and you likely wouldn't want to get rid of this in your actual code because your output is valuable. But just for science here, we're going to go ahead and do that. So I've gone in and I've eliminated all of the calls to this output subroutine. So if we go back in and we recompile the code and we generate another report, we're going to compare this timeline view, which now that I've removed the output call, you can see this timeline view, the wall time is decreased. It's now down to about 32 seconds. And also you can see nicely that the GPU kernels are just running pretty much continuously here. There are very few gaps in there. So a few other things I want to cover before we start talking about NSight compute and some of the GPU kernel optimization is another area that if you don't have a great idea on where to start from your baseline is this expert view, which it's just going to give you a couple scenarios that happen quite often when you're trying to optimize GPU code. And right now we're looking at the expert systems view and the GPU starvation. So if there was an instance of this, it would be flagged and it would give you the location of that problem and give you an idea of how to improve that. NSight Systems isn't the only profiling tool that you can use. There are a lot of others if you want to go and explore those options. There's some specifically for deep learning, machine learning. So DLProf is NVIDIA version, which is going to help with profiling and visualization for deep learning frameworks. TensorBoard is the TensorFlow equivalent, which give you better visualization if you'd like to do that. And then the NVIDIA tools extension, which is NVTX, is a nice intermediate step, I think, between the NSight systems and NSight compute analysis. And NVTX allows you to actually go into the code and set identifiers or set sections of the code where you'd actually just want to record that part of the code. But visually, this is really beneficial, and I'll explain a little bit in this code example that we're looking at. So the NVTX start range, you just have a label that within that timeline view, you'll be able to see for first label. And so between this start range and the end range, you'll just be able to tell that you're within that section of the code based on the label that you've created using NVTX. There's a really good NVTX walkthrough from our presenter next week, Jiri Kraus, who it's in C and C++, but if you'd like to go through that and look at what you can do with NVTX, I'd encourage that. So going back to NSight systems, this is the information that we'll be looking at to optimize our kernels in NSight compute. So if you zoom in far enough, you can actually see the specific kernel launch instruction calls here. If you hover over it, it'll give you some information, which right now, if you're not familiar with CUDA, probably doesn't mean a whole lot, but in terms of if you wanted to analyze this in CUDA optimization, there's some good information here for you. You can also go over to the events and right-click on the kernel as well and show in the events view. And that just gives you this textual timeline of all of these kernel launch calls that have occurred on the GPU. So from there, if you wanted to go in and use NSight compute, you can right-click on the actual instruction here. It'll bring a pop-up and you can analyze the selected kernel with NVIDIA NSight compute. It'll launch this window, and from there you can analyze that specific kernel in NSight compute. And with that, I'll hand it over to Daniel, and I'll take any questions that you might have while he's getting set up.
Thanks, Brett. Yeah, if you have any questions, feel free to set them into the chat. Otherwise, yeah, just let me switch over screens to the NSight compute section we have. So everyone can see this okay? No, the boxes covering up the window? Okay, I'm assuming we're all good. So I'm just going to keep on moving forward. Again, if you have any questions for Brett, add them to the chat, or feel free to raise your hand. But nonetheless, I'm going to go on with NSight compute section. So basically, we'll be talking on the next step in your profiling process, where NSight systems focused on a large-scale overview of your profiling process and how your program is running. NSight compute is able to dive deeper into individual kernels to see more specific performance metrics on those particular kernels. So in the again, we have our same workshop etiquette, so just skip over those. But to remind you, what is a profiler? These are tools that samples basically the various metrics and performance characteristics across the runtime of your program. So essentially, every few microseconds, nanoseconds in that kind of like frequency of analysis, the GPU is taking a measurement across its hardware of various conditions that the program is in during that particular time. And it's doing that, thousands and thousands of times a second. You can actually adjust that frequency of how many times it's sampling and making those measurements through these tools such as NSight systems and NSight compute. I'm explaining this in the sense that this is in fact like measuring consistently throughout the whole runtime of your program all this various information, and then basically these GUI tools that we were discussing, such as NSight systems and NSight compute, is compiling that information in a viewable, readable format for you to take insights from, such as understanding the overall runtime of the program and verifying what you've actually programmed is doing what you want it to do, as well as then just getting better understanding of, say, very specific metrics and performance understanding of your kernels on the GPU, such as how memory is being registers and caches, or utilization of the cores, SM, streaming multiprocessors in the case of GPUs, etc., memory throughput. Lots of different ways in which these tools are assessing performance throughout the runtime of your program. So again, you just saw on the left side, you have the NSight systems type view, and NSight compute is basically more of a kind of like a statistical list of various different metrics. So you have the timeline more view on the left, and on the right, you'll have a more kind of like list of and some displays of various different performance metrics and how those relate to each other. We'll go into more detail in terms of like some of those metrics that might be useful for your own analysis and optimization pursuits. So again, all this information, it's very well documented and extensively detailed on NVIDIA's own documentation pages. NSight Systems has its own documentation page, as well as NSight Compute. There's even a profiling guide that I encourage if you want to gain more skills within the specific context of profiling and optimizing performance of individual GPU kernels. That's a useful resource. There's even then a curated set of training resources that falls under the purview of NSight Compute and these profilers that NVIDIA curates. That includes like various an online forum you can ask questions into, or videos and other blog posts that are related to the profiling process. There's also an interactive step-by-step tutorial for optimizing an OpenACC code for this Berkeley GW many-body perturbation theory model. There's a GitLab you can follow, as well as in a recorded video on YouTube you can consult if you want an in-depth process for different approaches for optimizing OpenACC kernels. We'll look at a little bit of some optimizations we can take for the OpenACC implementation within Miniweather. But nonetheless, if you want a more in-depth coverage of that, feel free to consult other resources like that presentation by Max Katz. And again, that -H flag is always useful for when you want to just consult the information from how you can run NCU or NSys right within the terminal. So if you want to get that information right there, just add the -H flags, and that will print out a bunch of information for you to review to remind yourself of any other flags you might consider using. So again, at this time around, we were in NSight systems. We're now going to say we've identified an expensive kernel, and we're going to go into NSight compute to analyze that kernel's performance. Once you say improve a kernel, you can either like reanalyze performance with NSight compute, or you can go back to NSight systems, see how it changed over a timeline. And basically, the encouragement here is you have this iterative loop process where you go between NSight systems and NSight compute as many times as you like towards improving the performance and understanding the runtime of your model. At some point, when you get to a satisfactory level of performance, that's when you want to move on and maybe make additional efforts porting a different section of your code or some other model or some other project you might be working on. You can spend essentially a limited amount of time optimizing and improving performance of code, but at some point, we all have limited amount of development time. And so all these tools are meant to help expedite and make that development process faster, but nonetheless, some of the optimization process might take too much time. And so it's up to you to decide if it's worth your effort to continue to analyzing your model and further spending more time to figure out ways to improve it. So NSight compute, again, it's a CUDA kernel profiler, so it specifically focuses on specific kernels. And I was mentioning these are CUDA kernels. Even though you're running OpenACC or OpenMP, sometimes even Cocos code, which are basically just directives or some other interface for specifying a parallel region of your code. When you're working on NVIDIA GPUs, all of these methods are generating CUDA kernels regardless. So NSight compute is always analyzing a CUDA kernel. It's then curating performance statistics into targeted metric sections, as we'll see in the GUI later on, or a printout kind of like you would see from NVProf. And you're able to even select the amount of data collect from NSight compute and how it's presented. So that there's various ways to configure and change the way that these profilers are gathering data. Keep in mind though, especially with NSight compute, the more detailed analysis you do, the greater overhead that profiler will exhibit. So for example, in order to actually profile your kernel, it has to rerun it multiple times in order for the GPU to effectively collect the metrics in its limited metric sampling hardware it has within the GPU to actually produce the report effectively. So if you want the highest detailed report, that's going to take a large number of redundant runs of your kernels. You just want a basic report, the default one, you would only need a few, and thus then your overhead is much less. So all of these feature, a fully featured command line, as well as then user-friendly GUI interface. The GUI is particularly well suited for navigating the data in a very readable fashion, or much more readable than otherwise. So I encourage getting familiar with that and just exploring that in your free time. It's pretty fun to just kind of like look at the data and play around with what's going on. Within that GUI, the same, there's even then these contextual guided analysis tooltips that might show up. And these are particularly useful, especially for just trying to understand and get some quick hints or suggestions based upon expert developers that have contributed these sort of Python-based rules within NSight compute towards some best practices that they've encountered that can help guide you towards what an effective optimization next step might be. So, so in preparing your code for NSight compute, one thing that is important to often add is basically just one simple compile option is GPU line info. You don't necessarily need to use other typical debug flags you might have, like such as -PG or G or capital G. The line info flag is basically allows for the source or SAS analysis section of NSight compute to correlate performance information to specific lines of CUDA and or OpenACC, OpenMP code, etc. Basically, we have here, we just add this line info flag to the list of -GPU, and that basically provides additional information. And so we compile as normal. I mean, within the Open Miniweather app, you might use the make process, but I have this just expanded form of how we run the compilation here. Specifically, you have these options here, which might be important in terms of maybe your own exploration of this tool, say to modify the size of the problem or the simulation time. And notably, we don't need a large simulation time. We only need a small amount of time that at least covers all the kernels maybe we want to be analyzing. So you don't need to run the whole program in order to get these performance metrics out of into these reports. It's sufficient to run it very short. That way, you also are creating a very fast producing iterative cycle of analyzing your kernels in your code. So here's some NSight compute CLI options that are important. If you want to write out specify the report file name, just use the -O flag. If you don't use the -O flag, analysis will be summarized in std out. So if you want to use a GUI interface, you have to have that one in. If you want to force an overwrite of output file, you use -F. Two other important flags are -C and -S. Those will stand for launch count and launch skip. Basically, this sets the number of kernel launches to profile. If you don't specify either of those, the program will profile every single kernel it encounters, and that can be excessive and take up a lot of time if you're not careful. Launch skip, similarly, just skips a certain number of launch kernels. Maybe you want to skip into a specific kernel, however many you might need to get to a specific kernel. That's useful also for just letting the GPU warm up a bit. Oftentimes, initially run kernels perform a little bit slower than later kernels. To specify the amount of data collected, there's the useful flag might be -set. Some options there, often like detailed or full. Full is very extensive. In our cases below, when I show you the profiles later, that redundantly runs some of the kernels about 74 times to get all the data necessary in the full set. where the detailed set is about like 18 times. So keep that in mind. If you're having to run something 74 times redundantly, that's basically 74 times your typical runtime of your program. So if you need to be managing that appropriately, if you do want that very long form, a complete metric collection, such as from this dash set full flag. If you just want to limit and filter to a specific kernel, you can use the -k flag or under --kernel name. And you can then specify the exact name of kernels. You can use NSys from the previous section or previous profiles in order to see some of those names of kernels. In OpenACC, they're automatically named based off the subroutine they're within, as well as the line number. You'll see that in the profile reports previously that Brett was discussing. There's also, if you have NVTX enabled, you can enable that for NSight Compute, and thus then also filter profiles based on NVTX Regis. You might also say want to import the source within the report itself. That just allows an easier, streamlined way of going through the source/analysis section. In generating the NSight Compute report, we start with the final mini-weather OpenACC version that we had that's actually available through the mini-weather GitHub itself. This includes a collapse async clauses that Brett had just walked through again, as if you were starting from scratch, porting that code. We have the submit script in our folder for NCU_bash in order to run NSight Compute on mini-weather. Basically, it's similar sort of format of NSys. You prepend the executable with NCU and then the NCU options, and then you have your executable and any relevant executable arguments at the end. Again, you can review any of those options with NCU-H. So the profiles that we'll be running and analyzing will be using the -set's full flag so you can see all the information you get. If you use the default set, either not specifying sets or you use detailed, you'll see less information in the reports. But typically the default ones at least give you sufficient information to make initial steps. And if you need more in-depth analysis, you feel free to enable the more detailed or full set of metric collection. So if you run the qsub command like we have here using that bash script, this is how you might run it. We also pass in a variable NC reports name. Initially, you might say use the report name baseline. Here, which I'll discuss later, we actually make a small change where in terms of changing divisors to multipliers and see how that impacts performance. But we'll discuss that a little bit later. So if you're following along, feel free to shift and right click this file link here, or go to the file explorer and download the NC report. You can load it into the profile client in order to get further information in order to follow along in terms of our analysis. So again, depending on the option choice per set, you have different number of metrics measured. When you then get within the GUI, you feel free to look out for the guided analysis markers. There'll be little exclamation point warning signs. And these will basically highlight specific issues and try to suggest specific solutions you might look at. So some important sections that we want to be discussing, as you might see initially when you open the report, is this GPU speed of light section. So when it says GPU speed of light, it's referring to the maximum theoretical limits that GPU is able to achieve. So using all the streaming multiprocessors on the core on the GPU, or say achieving the maximum theoretical memory throughput. And basically, you can hover your mouse over any of the metrics that are then listed in the report in order to get a tooltip box describing what that metric is. But in this particular case, we're seeing that for this example screenshot here, the utilization of streaming multiprocessors, the SM percentage, and the memory throughput percentage are pretty equal to each other. So there's opportunity in either reconfiguring your workload in your kernel to distribute more work across a larger number of the SMs, such that all threads are constantly active, as well as then optimizing better, say, memory movement, say, onto the GPU or between caches within the GPU in order to improve memory throughput. So there's opportunity in this kernel for some improvement. It's sometimes difficult to make that improvement and are non-trivial to identify what exactly that improvement might be. But some of the further sections can help identify what that type of improvement might be in making that next step and actually making a change towards optimal performance. Another section that's important that will appear after you with detailed sets or more detailed set options like dash full is a roofline plot. So I've discussed that previously before. This helps you identify if you're in a compute-bound kernel or a memory-bound kernel. So if you're in the left side of this region under the slanted line, that means you're in a memory-bound region. And the right side, you're in a compute-bound region. So this lower level is essentially, the theoretical limit of double precision arithmetic on GPUs, and the higher one is for single precision arithmetic. That also points out some of the recommendations that the GUI might suggest is switching to single precision arithmetic. So if you're in a compute-bound region, you might be able to achieve even further performance just by going to single precision arithmetic, just since the GPU is optimized for that much better performance with that reduced precision amount if you're able to achieve that particular algorithm. So if you're in memory bound, you might benefit from assigning more compute operations per thread if possible. You basically want to saturate more compute given a smaller amount or constant amount of changing memory load store operations. But if you're in the compute bound region, that might require further analysis for identifying how to improve performance. That typically might involve checking for warp stalls or coalesced memory issues. Another section to look out for is the memory workload analysis section. This basically has this plot here that shows how memory movement is happening from the DRAM or CPU memory or the device memory on the GPU to then the caches on the GPU, and then down the line from there to the global memory or other memory objects within the GPU, and then actually then running on the kernel itself. So if there's imbalances here or inefficiencies in how this data is being moved, you can see that here. There's this little heat map of intensity for theoretical maximum throughput between some of these registers, as well as then you can see here these warning signs highlighting, giving you some guided analysis suggestions of what you might do to improve this. So in most of these cases, if you're having a memory movement issue that might involve a uncoalesced memory access, you might need to address. And so that can be something to think about and explore towards further improving your performance. See, let me double check what time I have left. Yeah, okay, 15 minutes. So in the last section that I find pretty important, and there's actually quite a few others that didn't cover, but nonetheless, and we might have time at the end here to go through an actual like using the GUI itself. Nonetheless, this last section is the source SAS section I mentioned earlier. And this helps identify particular instruction hotspots within your code. So on the left, you see here your actual source code, and this could be CUDA code, it could be OpenACC code. And the NSight compute profiler is able to correlate precise lines of code towards which assembly code is then run on the GPU, as well as then collecting various information about what is actually being done within each of those lines. So there's a lot of detailed information here. You might see on the right all these like kind of right and left facing arrows. That's basically showcasing registered loads and stores and dependencies along the runtime of a kernel, say from one line to the next in terms of when one store is say corresponding to another load, etc. But nonetheless, that might not be always important to look at. And part of the issue with NSight compute is there's a lot of information that's always presented. So it's helpful to at least start, like as you're exploring it, you start to develop some intuition of what's important things to look at. One thing that's important to look at in the source SAS counter, I like to look at just this sampling frequency there. That's usually the last column. I don't have it in the screenshot here, but that basically just shows kind of like a heat map of like where the time is most spent in the code. As I was mentioning before, these profilers are doing sampling across the full runtime of the program. And so if there's a spot in the code where it just happens to be taking up a lot of samples, that means it's just spending a lot of time there. So that means it's likely a inefficient portion of the code that should basically indicates that you want to be paying attention to why it might be performing slowly there. This particular view, if you go to this drop down here, you can then select source, or if you go to the bottom of the GUI itself, you can click the source lines that are suggested in the main details page. This will bring you to this view, and you can say navigate to the particular kernel that's like say you're analyzing, to check the performance and various other characteristics of that particular line of code. So another important thing to keep in mind when you're in this workflow with NSight Compute is you can't say, just like before we had NSight systems, we had a baseline and then we're gradually making changes to see how that changed the reports and different timelines and future reports. You can do that within NSight Compute itself, where you say, we have a baseline that we had run earlier, and then you can add that with a little icon here, add baseline. It's a little small. I'll show you a little bit in the interactive GUI itself. And then when you add baseline, you can then relabel that to whatever baseline number or text label you want to give it. And that's when you see like it makes a redundant plotting within that that one profile report you're in. But then when you switch to another profile report, you can then see that these now the baseline is then compared to your current profile report you're in. And that's when you can see how something may have changed over time in terms of like any changes you had made. So you can add as many baselines, so to speak, to your NSight Compute profiler in order to compare various different code modifications towards the performance of a particular kernel, and thus help you identify which one is actually the best, or say being able to identify when you make some change, what is actually changing then within the actual like detailed metrics of the report, and what's actually improving, what's maybe sometimes making worse. You can see here that when we switch from the baseline to our improved code, which I'll detail a little bit of how we did that, we actually got a reduced amount of SM utilization, but we got a much higher memory throughput utilization. And so we actually moved, if we look at the roofline analysis report, we actually moved from the compute bound region to the memory bound region, but we still stayed at about the same amount of performance of flops per second. So the actual kind of exciting part here when we did that change, which I'll discuss that in a little bit in terms of like, we actually were able to make it go faster. So when we looked at earlier that source section, we noted a hotspot at line 288. So basically by seeing that there's an issue there, we want to try to investigate that and see if there's a way to reformulate that line to either reduce redundant operations or refactor the overall algorithm in which it's contained to improve performance in that particular kernel. So the various metrics that you can say look through in the report can maybe provide hints towards why this line is a bottleneck. And there's multiple strategies that could be taken to improve performance, but we'll just focus on this singular one here that I'll point out. So in that particular line, some of the issues that we saw, some like warp stalls, you can click that link here within this presentation for descriptions of types of warp stalls as are defined within the GPU metrics, are happening these warp stalls are happening in that particular line. Essentially, a warp stall is where the GPU SMs have to wait for, like, say, an instruction to load or some memory movements or some other issue. And there's various different types of warp stalls. So there's quite a number of them. So if you want to look through those different types, follow that link. But essentially what's happening is that, if you recall the terminology of warp being like a block of threads, some of those threads within those warps, or maybe the whole block itself, just basically has to like wait around extra GPU cycles for it to actually do the work that it's being called to do. And that's just essentially wasted time in the GPU. So when you see something like that, that's something that you want to figure out why it's happening and try to adjust. Another issue we see in this line is that there's a much higher number of executions being executed compared to other lines in this kernel. So if we go back a bit, we can, this bar here, it's a little small. So if you have this open up in your own machine, this presentation, you can zoom in. The fact that this blue bar here exists basically means like a lot of instructions are being computed here, but there's far fewer being computed in other lines. So when we note that, basically we look at that line, we saw that there's like all these divisions by 12 everywhere. And actually in IEEE computational arithmetic, as is often converted then onto CPUs, division is typically more expensive than multiplication. So a way to which that we actually can improve performance on this particular line is to simplify it by getting rid of the divide by 12 on each of these constants that were essentially from this stencil we're loading in on this vowels line, and replacing that with basically a a long number that's essentially equivalent to dividing by 12. We're basically doing reducing 4 divide operations, replacing it with 1 multiply operation. If you want to download the report that has that particular change, or you're more than welcome to change it yourself or do other changes. But nonetheless, the report that reflects this particular change is here. So feel free to download the report and open up in your own time to follow along. So yes, so basically when we did that change, we basically got this report out back where we got improved performance. And the significant part here is actually that the time, and it's small text here, so I hope it zoomed in better, but I think the image got mangled. Nonetheless, that time reduced from 6.2 milliseconds to 3.5 milliseconds, essentially. So we got nearly 50% improvement on just that one kernel by replacing those division operators with that one multiplication operation. So these are the type of using NSight compute can help you make those sort of assessments towards those types of improvements. And so as a exercise for people to do following this workshop, you're more than welcome to say, play around with the problem size and see how that impacts performance across kernels and analyze what that exactly means. Maybe check if there's an optimal problem size for optimal SM utilization and memory throughput. Another way is, take the same approach as before, find specific lines of code and see if you optimize or refactor it towards improving performance. Maybe you want to coalesce memory or access or rearrange the order of loops. Those are different styles of which you might try to improve performance. And I encourage you to explore that and figure out what you think works best in some of these different cases. So with the extra time we have, and so we have about 5 minutes, feel free to ask any questions, but I'm going to switch over quick just to show you the actual profiler itself in real time. While we have you here, just to show you here, can everyone see the profiler window now?
Yeah, we can see it.
Okay, so yes, in this case, we have it basically as before. We were just in screenshot mode, but now now we have the profiler set here. We have the comparing to the baseline we had previously. Sorry, this other window that popped on my screen. I'm trying to get rid of it. And so, we can scroll through and see the reports I already discussed. We have our main GPU speed of light throughput report. We have the roofline analysis. We also have compute workload analysis. This one discusses, what types of operations are done most frequently. We either have floating point operations or ALU operations or FMA operations. And again, you can hover your mouse over any of these, and this will give you a description of what exactly each of these mean. So this is a fuse, multiply, add, for example. You have the memory workload analysis section I mentioned. But again, there's more of these, and I don't necessarily have time to cover all of them. Feel free to explore in your own time or refer to the kernel profiling guide. But the one at the end here, this source counters section, that's the one I was mentioning in terms of being able to go then to the source code of your code and correlate to the actual performance of particular lines of code. So for example, if you go to which line we changed information at, so we were at this line. When you click on it, you actually then also highlight all the different assembly code that's essentially running on the GPU, and the representation of that for this particular change we made. If you go back to our baseline, go to that same section. So basically click on down here. Apparently, there's also some issues down here in this section, but we're going to focus on this line here. This one was also a hotspot. Again, you had that large number of stalls happening here at that line, as well as a massive number of instructions executed. And if you look at the source code here, there's a lot more assembly code just because of all these redundant divide by 12s happening. And again, that's part of the reason why division operations are less optimal compared to multiplication operations. So if we go back to our change version of the code that we now have, where we instead multiply by that singular 1/12 essentially over here, we have far fewer operations taking place in the GPU just because of that singular change. That is correlating to a much reduced runtime for the when we moved division and replacement with multiplication, and thus then we see that again we went from 6.2 milliseconds to 2.5 milliseconds. So these are the kind of steps you can take towards utilizing the profilers for optimizing your code. But nonetheless, thank you for your time today. And if you have any questions, feel free to let me know. That's all I have so far. But if basically at the end, if you'd like, again, all these resources exist, so feel free to consult them in your own time. But let me know if you have any questions, and we can stick on for another 5 to 10 minutes or so just to have conversation. But thanks again for your time.